I've always found it amusing that the canonical story of technology disruption had nothing to do with silicon, PC, SaaS, or AI. It involved steel. The late and great Clayton Christensen mentioned the Minimills in his 1997 book, The Innovator's Dilemma. And he wrote that mini-mill steelmaking was a disruptive technology, one that emerged like the Mongols to take down a complacent empire. Well, was that what really happened? The whole thing has always fascinated me. In today's video, the conquest of the mini-mills, a story of pure disruption. This video is brought to you by the Asianometry Patreon. The traditional steelmaking process starts with iron ore as raw material and coal for energy. It begins with crushing and sintering the raw iron ore, creating porous lumps that prepares it for the next step. The coal, meanwhile, is also crushed and heated up to high temperatures inside an oven to create a high-carbon, hotter-burning derivative known as coke. Then both the sintered iron ore and the coke are combined inside a blast furnace and blasted to produce pig iron, a high-carbon intermediary product. Pig iron contains too much carbon to be industrially useful, so we must lower the amount of carbon and other impurities. Two early ways of doing this were the Bessemer and open hearth processes. The Bessemer process is the first modern steel mass production process invented in the 1850s. Air is blown up through the bottom of a melt-filled converter shaped like a European pear, removing carbon and impurities via oxidation. Bessemer is fast, but produces steels of varying quality, so in the 1880s came the open hearth, which cooked the melt over longer periods for better quality control. There is a third type of furnace, but I'm going to set it aside for now. It arrives much later. Once the molten crude steel is prepared, it needs to be cast into a useful shape. The easiest and most traditionally used form factor is the ingot, but there are other desired form factors like blooms, billets, slabs, plates, and wire rods. It depends on the end use case because customers want different shapes and are willing to pay for it. The defining characteristic of an integrated steel mill is that this is all performed within a single facility, reducing the need to cool and reheat the bars from step to step. The city of Pittsburgh became the center of America's steel industry because its location let it receive both iron ore from the far end of Lake Superior and coking coal from the rich coal fields nearby. The most successful steel companies then integrated themselves vertically through the whole supply chain from iron ore to coking coal to the ships carrying them. Doing so made them the lowest cost providers. In 1901, the country's two largest steel firms, Carnegie Steel and Federal Steel, combined to form U.S. Steel, making half of the country's steel. U.S. Steel's size, cost, efficiencies, and abilities to subsidize finished products could have allowed them to monopolize the industry via price war, and Carnegie Steel's competitive people were apt to do that again. But U.S. Steel's second chairman, Judge Elbert Gary, instead sought peace by raising prices high enough to allow competitors to survive. Gary's umbrella, as it was called, ended the cutthroat price wars of the 1890s and gave U.S. Steel price leadership and control of the market. The umbrella fell apart after Gary's death in 1927 and the economic collapse of the Great Depression. The company struggled through difficult times, which finally ended with World War II. The U.S. government funded new steelworks for U.S. Steel to make steel plates for warships and armor plate for tanks, vastly expanding capacity, especially on the West Coast for the war's Pacific Theater. After the war, the American integrated steel industry, or Big Steel, stood at the very peak of their powers. In 1945, America made 80 million tons of steel, a stunning 62.4% of the world total. U.S. Steel, as Big Steel's biggest steel, reigned supreme. Now let us start a new arc. Imagine two electrodes held close to one another, but with an air gap in between. Normally, air is a good insulator, but if a high enough voltage is applied, then free-floating electrons in the air start moving from one electrode to the other. When they go, these moving electrons hit other atoms, knocking their electrons loose and ionizing them. This just adds more free electrons flying around. This goes on, creating a whole chain reaction that eventually turns the air between the electrodes into a conductive plasma. This region of plasma is called the arc. As those electrons and ions travel inside the arc's plasma, they knock into their peers, generating kinetic energy that eventually leads to heat and very bright light. This is called Joule heating, and it is the principle behind hot plates and the super hot NVIDIA B200. Here, it can create temperatures anywhere from 6,000 to 20,000 degrees Celsius. Experiments with the arc were being done all the way back to 1815. Then, the English scientist William Pepys put some diamond powder in an iron wire and passed a current through the wire. The wire glowed red with heat, absorbed the diamond powder, and became steel. Pepys' goal was apparently to prove that diamond was really made of carbon. The idea of using an electric current to melt metals down, however, persisted, but remained impractical for over half a century because the only power source were weak batteries. The invention of the dynamo in 1866 made it easier to generate a more powerful current. In 1878, William Siemens built a furnace for melting down metal with a current. The first version was a vertical furnace with one of the electrodes placed on the bottom. The metal to be melted down is placed on that electrode. A second electrode is lowered into the furnace until it produces an arc, heating up and melting it. The electric arc furnace first proved its worth in aluminium. In the mid-1880s, two brothers, Alfred and Eugene Coles, built electric arc furnaces based on Siemens' designs to produce aluminium alloys. Their work was called the Cowles furnace. Then, in 1886, the American scientist Charles Martin Hall, a future co-founder of Alcoa, and the French scientist Paul Héroult independently invented the process to turn aluminium oxide into pure aluminium. The Hall-Héroult process dissolves aluminium oxide in a special salt and passes a powerful electric current through the solution. It is the foundation of the modern aluminium industry. Héroult, a wild and woolly womanizer whose inventions came out of random flashes of inspiration, designed a special furnace to do this, something akin to the original William Siemens design with one electrode on bottom and the other on top. The bottom electrode was lined with carbon. During operations, the top electrode is lowered into the molten metal. A current is thus passed through the liquid metal. This initial design was flawed. Having carbon on one of the electrodes caused it to quickly dissolve into the melt, tainting it. Ultimately, it was not a good idea to have the melt be part of the circuit. So after some trial and error, Paul redesigned the furnace by placing the two electrodes above the melt, essentially separating the arc's heat source from the liquid metal. Now that the current no longer travels through the melt, it can no longer contaminate it, enabling more delicate chemical reactions. This new design was at first used to make pig iron from iron ore, and in the 1890s people tried to use it to produce steel directly from iron ore with little success. But by at least 1906, people had learned that Héroult's furnaces had an interesting benefit. Because the heat source is mounted up top, you can put special mixtures of absorbing chemicals like sand or lime, called slag, on top of the melt. The molten slag stays on top of the melt, absorbing impurities like sulfur or silicon. It can then be skimmed off the top of the metal, leaving behind a steel purer than its inputs. So, Héroult's furnaces decoupled the quality of the steel output from the quality of its inputs, and this was a big deal. One reason why Carnegie and US Steel so dominated the industry was its access to cheap, high-quality ores in the Mesabi Range in Minnesota. It enabled the company's quality and low cost. But with the electric arc, pure or impure scrap alike can be loaded into a furnace and melted down in 2 to 3 hours and produce high-quality steel. Like, as they say on LinkedIn, this changes everything. Or not quite. Electric arc furnaces were widely used in the aircraft industry to produce things like valves and ball bearings, but in the steel industry it remained a niche tool for refining steel or producing specialty alloy stainless steels, higher tier metals that have to withstand higher strain or difficult conditions. The perception being that the electric furnace suited them because it took longer to cook. Here's an example. One of the first steel companies to adopt electric furnaces was the Northwestern Steel and Barbed Wire Company in Illinois. In the mid-1930s, they installed two 10-ton electric furnaces to produce stainless steel for their barbed wire fences, largely due to U.S. government restrictions on adding more integrated steel capacity. Adverts and newspaper articles of the time emphasized the superior quality of their fences' quote-unquote electric steel, that it is denser, tougher, thicker, and more pleasing to you. So that was the electric arc furnace, a specialty tool for niche steels. But for their bread and butter steel, Big Steel used either the aforementioned Bessemer or open hearth processes, mostly the latter. But the idea for alternatives flapped around. A 1940 Pittsburgh Sun article examining the prospects of a large steel industry in the American West noted, "There remains the idea that cheap electric power will bring about the development of a northwestern steel industry on a large scale. Theory is that electric furnaces would take the place of open hearths, and it's true that cheap electricity makes it possible to melt and refine scrap steel into high-quality alloy or stainless steel at a cost which compares favorably with open hearth costs." Sounds familiar, no? But the article goes on to insist, "But the blast furnace is still an essential part of all the large integrated steel plants which are the primary producers of the great bulk of the nation's steel, and so far it's still much cheaper to produce ordinary steel, so-called carbon steel, using the blast furnace to produce the molten iron, and the gas produced in the blast furnace to help fire the open hearths which refine the raw molten steel and scrap steel into the grade of steel desired." Some people call Northwestern the first Minimill, but to me that's a bit retroactive. Northwestern used electric arc furnaces, yes, but they didn't have what makes the Minimill the Minimill. That thing is continuous casting. After the molten steel is done, it needs to be cast, an energy-intensive process. Take stainless steel wire, a barbed wire precursor. After the electric furnace produces the molten stainless steel, the melt is poured into batches of ingot molds, which look like popsicles, and cooled down. The 1,000-pound ingots are then reheated in a furnace or soaking pit to over 1,000 degrees Celsius. This softens them enough to be squeezed and rolled into long triangles called billets. The billets are cooled down. Workers then grind off the billets' surface to remove impurities, oxidation, and other imperfections. Such impurities tend to collect at the steel's surface as it cools down. Then the billets are reheated and rolled into wire rods, which are semi-finished steel wire forms. It's shaped like wire, but it is still too thick for use. So, in the final step, the wire rods are cleaned or pickled in an acid bath. Then it is reheated and annealed to soften up before being drawn to reduce their diameter. Voila, wire. A very interesting process, and there's like so much waste. Note all the times the steel has to be cooled down and reheated. Imagine all the energy costs. Or have the surface scraped or burned off. In some cases, as much as 30% of the steel is lost from impurity cleaning. Like, why do we need to cast the ingots in the first place? That is the idea behind continuous casting. We go directly from liquid steel to billet, skipping the ingot process step. The idea has been around. Henry Bessemer, creator of the Bessemer process, had done something similar with glass and wanted to apply it to steel. But for a long time, the high temperatures involved, as well as issues relating to the steel sticking to the mold, kept it from hitting the shop floor. Then in 1933, a German named Siegfried Junghans published a type of open-ended and water-cooled mold. You pour molten steel into one end, and partially cooled shaped steel emerges out of the other. Cut it off, and we got a billet. Think of it as kind of like a pasta extruder, but for hot molten steel. Junghans died in 1954, having perfected his techniques for brass and non-iron materials. An American financier named Irving Rossi acquired Junghans' patents from his widow, adapted it to steel, and founded a company called Conquest to sell the machinery in the US, Europe, and Japan. By the way, I must note here that continuous casting is a very diverse technology with many fathers. I skipped various little discoveries and breakthroughs in Europe and Japan in the interest of brevity. In 1954, a Canadian metallurgist and serial entrepreneur named Jerry Heffernan founded a small steel mill in Alberta, Canada called Premier Steel. Premier Steel supplied thin steel rods to Alberta's growing oil industry. Heffernan knew Irving Rossi, and though Premier still cast most of its steel into ingots, in the late 1950s, Heffernan commissioned Rossi to build a continuous casting machine to make billets for rods. The results were immediately spectacular. A large Canadian steel rival, Stelco, noticed Premier Steel's progress in a critical market. So in 1962, they acquired Premier, giving Heffernan the money to fund another startup called Lake Ontario Steel, or LASCO. With LASCO, which started operations in 1964, Heffernan took another step forward. No ingot molds on the shop floor at all. Liquid steel was either continuously cast into a semi-finished shape like a billet or returned to the electric arc furnace. We generally consider LASCO the first real deal mini mill. It's not clear who decided to call it that, but the name is fitting. It ditches the mining, coke furnaces, blast furnaces, and all the steps prior to steel making. So it's just scrap steel, electric arc furnace, continuous casting, and a mill to finish the steel. The financial advantages of running this light are immediately undeniable. In 1969, the Integrated Steelworks facilities for producing 4.25 million tons of raw steel a year cost about $400 million. The cost of 8 150-ton electric arc furnaces that can theoretically produce the same amount of steel, less than $60 million. Minimills began small. LASCO made about 200,000 tons of steel each year, but others range from 40,000 to 300,000 tons. To compare, the big integrated steelworks did millions of tons annually, and the limits of the casting machine let them basically just make rods. Still, LASCO inspired copycats. The Minimills' small size, low startup cost, and them not being tied to mineral supply made it possible to put them closer to their end users, a critical selling point that let them be more responsive to customers. So Heffernan partnered with the food giant Cargill to build another mini mill in St. Paul, Minnesota called North Star Mill. There in 1967, Heffernan met Ken Iverson, president of a then almost failing company called Nucor Corporation of America. The company that is now America's largest steelmaker has a famously strange history. They were founded in the 1900s by Ransom Olds, the creator of the Oldsmobile, and given the initial name REO Speedwagon. Just kidding. REO Motors. REO Speedwagon is a band from the 1960s that played some of my favorite songs. REO Motors made cars and trucks until business lagged after World War II. After selling both businesses, they tried to liquidate, but another company took over and merged its remains with a small nuclear services company, changing the name to Nuclear Corporation, or Nucor. Nucor then tried to acquire various businesses in a vague attempt to capitalize on the growing energy boom. U.S. Semiconductor, equipment leasing, office copiers, none of these made sense, and the whole thing was a bit of a mishmash. By 1965, all these acquired businesses were failing, except for one, Volcraft, which produces steel joists. What's a joist? Think something like a truss for construction. Anyway, the Nucor board was rightly voted out for lighting this flaming dumpster fire, and Volcraft's head, Ken Iverson, was made president of the whole company. Iverson was still in his 30s and took the job essentially because nobody else wanted it, like that last sushi at the all-you-can-eat buffet. But Iverson turned things around, selling off everything and restructuring the company around Volcraft, which ran small and lean with non-unionized workers. However, Volcraft's only steel supplier was raising their prices, so Iverson started looking around for a new alternative, and he found his answer at North Star Mill in 1967. Iverson then, in a bet-the-company moment, borrowed $6 million to build Nucor's first steel mill in Darlington, South Carolina, at first to make steel just for Volcraft, before starting to sell billets to outsiders within a year. By the end of the 1960s, Minimills supplied about 5% of the American steel market, but they were confined to only their local region and remained very small. Darlington maxed out at about 80,000 tons a year. and they only made low-end products like reinforcing bars for concrete or light shapes for construction like the aforementioned joists, hardly a danger to Big Steel. To Big Steel, the big danger was coming from abroad. In 1958, imported steel was less than 3.1% of American steel consumption. Then in 1959, U.S. Steel tried to remove a clause regarding changes on work team sizes. 500,000 workers walked off the job for 116 days, halting 85% of the industry before President Eisenhower eventually orders them back to work. The 1959 steel strike opens the door to foreign imports, many of which came from Japan. Immediately after the war, Japanese steel production was 7.3% of its pre-war peak. But the Japanese steel industry quickly rebuilds thanks to the outbreak of the Korean War and government support, which included a 3% export subsidy, ample bank credit, and a tariff of about 10 to 15%. Starting from greenfield also allowed them to aggressively adopt a critical new technology. Recall earlier I mentioned that after the Bessemer and open hearth processes, there was the third process. That was the basic oxygen furnace, or BOF. BOF blows high-purity oxygen through the melt at high speeds, cutting batch production time from 8 hours with open hearth to 45 minutes without compromising on quality. It was invented in Europe, but the Japanese rapidly adopted it, giving them massive scale and throughput advantages. These, plus the fact that the average American steelworker made 7 times more than his Japanese counterpart, help open a 40% cost gap between Big Steel and the Japanese steelmakers. In late 1968, with steel imports at 17% of the market, the Nixon government negotiated Voluntary Restraint Agreements, or VRA, essentially getting Japan and West Germany to agree to limit their steel exports by tonnage. There is some disagreement about whether those countries obeyed their limits, but it looks like foreign steelmakers on the whole responded by shifting to higher-priced steel markets. So ironically enough, the VRA probably benefited the Minimills most. In its first 2 years, import share of the Minimills' low-margin steel markets fell from 25% to 14%. Big Steel, on the other hand, did not use the VRA's 3 years, later extended to 6, to invest. In 1968, American steel companies invested about $2.37 billion into actual steel work. 3 years later, investments actually receded. What's going on? Why aren't these companies taking advantage of their grace period? One reason was profitability. Big Steel looked at the growing steel glut in the rest of the world, ran the numbers, and could not justify a positive ROI. And when you factor in the then mounting environmental costs associated with integrated steel construction, U.S. Steel would not even be able to pay back the interest. So instead, the big steel companies merged with each other or diversified, the corporate version of strapping on parachutes and life jackets. National Steel started producing aluminum, which generated record profits for them. Another steel company, Armco Steel, diversified into insurance, engineering services, grinding balls, plastic piping, and financial services. They later dropped the steel part from their name entirely. And as for U.S. Steel, in 1968 they bought Armor Chemicals, a chemical fertilizer company, and built up a chemicals business around it. They also talked about doing plastics. Then in 1969 they did the Asian business thing and started a real estate development business. A year later, they built 2 apartment buildings for Walt Disney World of all places. None of this really caught on. Whatever money was spent on the steel plants was spent poorly. Rather than building leading-edge greenfield plants, U.S. Steel invested in piecemeal improvements at their aging existing plants that were too little, too late. They also paid dividends. Between 1970 and 1976, American steel companies paid over 40% of their after-tax profits in dividends. They wanted to give people a reason to hold their stocks as the diversification efforts progressed, but it doesn't look good in retrospect. Finally, and perhaps most significantly, in 1973, Big Steel struck the experimental negotiating agreement with the labor unions. Labor gave up the right to strike in exchange for lucrative benefits. With ENA, the companies bought peace, but at a rich and ultimately unsustainable cost. The VRA finally ended in 1974, but the U.S. steel industry nevertheless showed optimism about its prospects, showing profits at a post-war high. Some of this was due to the diversification, but also the 1973 OPEC embargo initially caused panic steel inventory buildup and soaring steel prices. Such rising prices contributed to inflation. But shortage fears were over by 1975, and the economic slowdowns that followed caused world steel demand to slump. The steel imports returned with a vengeance, surging from 13.4% in 1974 to 17.8% in 1977, and then 18% in 1978. By then, the world trade situation had changed to the point where the US government was reluctant to add further protections without risking other industries wanting the same and then triggering a global trade war. Finally, the Carter administration did the Trigger Price Mechanism, or TPM. TPM sought to detect and defeat dumping, which the American companies increasingly accused Japan of doing, using a complicated scheme that set a price floor on steel imports calculated to be quote-unquote too low. Well-meaning but Byzantine and ultimately unworkable, the American steel companies abandoned it in the late 1970s in favor of suing foreign producers. But unlike the foreigners, U.S. Steel and the rest of Big Steel could not bludgeon the mini-mills with nationalism. They had to compete. More mini-mills were built throughout the 1970s, and slowly they expanded their share of the market from 5% to about 12%. This was in part due to product lineup expansion. Nucor's first plant in 1968 made steel bars from reinforcement concrete, but they soon expanded into rods and angles, as well as expanded beyond their core regions. Despite this, mini-mills stayed focused, offering at most 5 products, but doing them well. This is in contrast to the integrated steelmakers, which offered a smorgasbord of products, but at varying and often disappointing levels of quality. Meanwhile, the mini-mills retained their favorable cost structure against integrated steel. A 1980 analysis found that a mini-mill cost about $150 to $300 in 1978 per metric ton of annual capacity. An integrated steelmaker, on the other hand, costs about $956 to $1,500. A mini-mill can also be built in just 1 to 2 years, as compared to the integrated facilities' 8 to 10. As for labor, the mini-mills inherently need less labor, but they also aggressively adopted automation, in part because each mill was built so quickly. By 1980, a mini-mill could produce wire rod with 3.51 man-hours per ton, an integrated steelmaker 6.45 man-hours. It's important to note that Nucor and other mini-mills like Chaparral ran their operations in such a way to discourage unionization. They kept their team small, removed hierarchical divides between white and blue-collar workers, paid well, and recruited from cheaper rural areas and right-to-work southern states, mostly farmers. Iverson has before said that the benefits of being a non-union manufacturer have little to do with money, and that the true upside is being able to make changes quickly and be flexible. Definitely true, but I also can't help but note that in the mid-1980s, workers at even the larger mini-mills earned $17.50 per hour at max productivity. An integrated steel mill worker, $22.50 on average. U.S. Steel and others always perceived the mini-mills as weaknesses to be a reliance on cheap electricity and scrap steel. Scrap steel, most of all, being up to 50% of cost. It was assumed that scrap steel prices would rise and price them out, but that never happened. Scrap steel was volatile, but stayed cheap even during the 1970s, perhaps due to a robust scrap recycling network in the United States. So even after trade protections ended, the mini-mills steadily took share from the steel imports in their markets like rebar throughout the second half of the 1970s. In 1981, imports captured 18.9% of the total steel market, but less than 9% of the markets that the mini-mills operated in. In 1979, Big Steel employed 453,000 people, and domestic shipments were above 97 million tons. ENA, the controversial 1973 labor agreement, secured unprecedented gains for American steelworkers and extended labor peace for companies, but at a cost. By 1980, those Big Steel workers enjoyed a 65% wage premium compared to other American manufacturing workers. This could not hold. I briefly hinted at a world glut. In the mid-1970s, the Japanese started exporting steel technology to developing countries. So where before Big Steel only had to deal with imports from Japan and Europe, now they had to tangle with steel imports from Brazil, the People's Republic of China, South Korea, Taiwan, and more. And ironically enough, many of these steel efforts were funded with American capital. And unfortunately, steel demand back home simply did not grow as expected. In 1975, trade associations predicted that steel demand would rise to 150, 160, 180 million tons by the 1980s. But the changing American economy caused those numbers to fall far short. Once upon a time, the USA's biggest, richest companies made things like cars, planes, or petroleum, things that required a lot of steel. Now the growth was coming from companies in information technology, consumer goods, or entertainment, none of which use as much steel. Manufacturing output in America rose 7% between 1979 and 1984, but those goods were computers and IT equipment, not tractors and railroad equipment. Even steel's traditional customers were using less of it now. Between 1976 and 1986, the U.S. automobile industry cut steel consumption nearly half, from 23 million to just 12 million tons. Why? Just one word: plastics. In late 1979, new U.S. Steel chairman David Roderick announced that U.S. Steel would close over a dozen unprofitable plants, laying off 13,000 workers. They also sold off many heritage assets, like the company's shipping fleet, its famed civil engineering firm American Bridge, and massive coal and limestone fields. And then, in December 1981, with steel imports and the Minimills each reaching 25% of the market, U.S. Steel made its biggest diversification move yet by acquiring the oil giant Marathon Oil. America's biggest and most iconic steelmaker literally just gave up being a steelmaker and decided that they were going to be an energy company. They renamed themselves to USX in 1986. By 1989, Big Steel employed just 150,000 workers, a staggering 67% decline from only 10 years prior. The Minimills' low startup costs, in some cases 10x lower, made it easier to get into the space. The competition intensified and got such that a few mills closed in the mid-1980s, but it forced the good ones to go upscale, and then suddenly, in the late 1980s, the barbarians had breached the gates and were breaking into Big Steel's backyard. For a long time, Minimills could only produce bars, angles, or rods. Big Steel soon withdrew from those markets, retreating to the flat-rolled metal markets, thin, flat steel sheets used by appliances and car makers. These remain one of Big Steel's last lucrative strongholds. That is because producing these thin sheets of steel required first producing a 6 to 12 inch thick slab. The slab is cooled, cleaned, and inspected before being reheated and rolled flat by a sequence of up to 9 giant rollers. The line might stretch over a quarter-mile long, representing a capital moat no mini mill can cross. Or can they? In 1986, a Nucor executive traveled to Germany to review a new process called compact strip production, invented by SMS Semag in Germany. What SMS invented was a new 2-inch nozzle that produced thinner 2-inch thick metal slabs that reduced the size of the facilities by half, cut capital costs by 60%, and reduced energy costs by 30%. Many other steel executives had seen what SMS done, but they all dismissed it. Nucor instead poured some $275 million into a new facility in Crawfordsville, Indiana, implementing the first thin slab caster, as it was called. It worked. Thin slab brought the Minimills into the U.S. flat-rolled steel market, which in 1988 numbered 35 million tons, or 50% of total shipments. Nucor's competitors piled into the industry too. In 1995, $3.5 billion was invested into flat-rolled steel Minimills, producing 3 million tons. 5 years later, production had surged to 20 million tons. The integrated companies responded with massive upgrades of their own, upscaling to the final bastion, strip steel, narrow and thin strips of steel used for precision items, electronics, or even razor blades. So of course, Nucor again strikes a joint venture with the Australian mining giant BHP, licensing a newly discovered process to start casting strip steel. Their first strip steels began shipping in 2002, though there are problems with yield. Since then, the integrated steelmakers and Minimills are battling it out in the sheet and strip markets. The Minimills are making progress, but the old folks are holding on, perhaps thanks to scrap shortages. It is interesting to note that so many of the technologies to enable the mini-mill boom came from outside of the United States. Continuous casting came from Europe. The first real mini-mill was founded in Canada. Yet mini-mills didn't quite take down the big integrated companies abroad in the same way they did in the United States. Perhaps one major reason for this can be found in the 1983 collapse of a German mini-mill steel empire owned by the entrepreneur Willy Korf. Korf bought into the mini-mill concept immediately in the 60s and brought it to Germany, only to find that Germany's banks were less than willing to fund his idea, and the big integrated steel incumbents banded together to control scrap prices to price him out of the market. So he instead brings it to the US and earns enough from there to fund a few mills in Germany. But then in the early 1980s, a crisis hit Germany's steel industry, particularly in the area of Saarland, the Saar steel crisis. Korf's small steel empire collapses due to insolvency. Korf later finds out that his integrated competitor, despite being far less efficient, was being kept alive with billions of dollars worth of subsidies, leading to him suing the local government. His firm was later rescued by state guarantee and lives to this day. I guess my point is that disruption in the market presumes that the players in the market are all playing by certain rules. Who cares if your mini-mill is 10 times more effective than the incumbent when the incumbent is getting billions of free euros from the government? The US government brought a rather lighter touch to its steel market throughout the 60s, 70s, and 80s, probably less by principle and more by policy paralysis. Their action allowed the mini-mills and the imports to apply sufficient market pressure to cut down an iconic but inefficient steel giant. The social consequences of such a reduction we continue to see to this day. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.